Okay, so good afternoon again. Sorry, good morning, everyone. Welcome to APNIC eLearning web class. Today is the 25th of January in 2017. It's 11 o'clock in the morning from Brisbane in Australia, where I'm conducting this class. I know some of you probably are from the Pacific, some of you from maybe Southeast Asia or South Asia, or maybe somewhere around the world. So depending on your time zone, good morning or good afternoon to you. Now, this session is, as you can see, about securing DNS. So in this class, we will be talking about a few things, of course, that's related to the DNS infrastructure, the possible vulnerabilities and issues that you can find with that, and also how we can of course, add some security measures and security protocols on top of that. Now, before going into the details, just to quickly introduce myself, my name is Sheryl Hermoso. I am part of the training team. I think some of you know me from the session. I can recognize some names there. As part of the training team, I have conducted a lot of trainings, either face-to-face or e-learning to members of the internet community in the Asia-Pacific region, which is the coverage area of APNIC. APNIC, as you know, is the Asia-Pacific Network Information Center, which is the internet registry for our region. Now, we do have this online sessions for those that cannot attend our face-to-face workshops. And we do topics that are, of course, related to internet technologies, things like routing, BGP, MPLS, things about related to security as well, such as network security, DNS and DNS security as well. Internet resource management is one of them, and of course, IPv6. Now, for this session, this runs for 1 hour. Sorry for the long introduction, but yeah, I just need to clarify that this will run for 1 hour, and at the end, I will be asking you to fill in a short survey. I have the link at the end of the slide, so I hope that you will help me fill that in. Now, I do like to encourage questions, so if you have any questions, even though I'm in the middle of talking, please feel free to write them down on the chat. That's the way that you can communicate with me. Okay, I cannot give you a microphone because we also have people attending the session who have issues with bandwidth. So to save that, we only allow questions coming from the chat panel. So as soon as I can see them, I'll try to answer. Okay? So with that out of the way, let's start with our topic at hand. As I've said, we will be talking about DNS and DNS security. So of course, to go through this topic, we will look at the DNS infrastructure and identify the DNS vulnerabilities that are associated with it. What are the possible attacks that can happen to DNS? How important is DNS? And what information or what part of the DNS infrastructure should you provide or should protect? Okay, we will look at securing name servers, particularly by looking at these two protocols: transaction signature, TSIG, and DNS security extensions or DNSSEC. We have a separate session that discusses just DNSSEC. I think that's the next one after this. But the purpose of this one is to tie everything together, okay, and identify which ones can be protected with TSIG, which ones can be protected with DNSSEC. I also have a few things at the end about the use of DNS in adding security to the rest of the network. Okay, so let's go to the details. First of all, a little bit of security background. Well, you know what DNS is about. DNS stands for Domain Name System, which is a utility or a tool that's used to map IP address to domain names to IP address, and maybe a few other different types of information. But at the very basic, it's IP to domain, domain to IP. We know that it's an important protocol. It's a very simple protocol, to be honest with you. Okay, it has a tendency to be a very busy server. Okay, if you have many connections, many users for that network, it can be very busy. If you're hosting a lot of domains, if you're opening it up to the public, it can become very busy. At the same time, if it's operated on a small enterprise network, okay, but you have your own domain name system, okay, DNS server, then maybe the traffic is not that much. So depending on the purpose, depending on what it's hosting, okay, a DNS server okay, can be pretty stagnant, or it can be a very busy server. DNS servers are important in the entire network infrastructure. We sometimes call it as a network protocol. Why? Because it aids in the rest of the networking functions, right? So it's important that we provide protection on DNS. I think some of you have seen on the news, okay, over the past, I'd say 3 to 5 years, there have been many attacks that is targeted towards DNS servers. Why is that? Because of what I told you about. DNS provides you with that stability in the network. And if that is attacked, there are many things that can happen. One, it can influence the way you access the network. If it gives you wrong information, you go to a wrong server. Okay? Another, if it's not available, then it interrupts the rest of your operations as well. Okay, you cannot access the DNS. If you have customers that want to reach you, how can they? Okay, your DNS server is not available. They don't know how to get to your, maybe your server or your website and stuff like that. Other security issues that can come up with this: using reverse DNS to impersonate hosts. Someone can pretend to become this by influencing the content of your DNS. Others, software bugs, maybe buffer overflows. This has got to do with the DNS software that you're using. And one that is quite common during the last 3-5 years, I guess, is cache poisoning. Adding inappropriate data into the cache. I have some slides here that discusses this in more detail, so let's skip that for now. DNS Protocol Vulnerabilities. I think I've already mentioned quite a lot about this, so let's just go through this very quickly. DNS data can be corrupted as it transfers between primary servers, resolvers, or forwarders. I guess if you look at this slide, think of ways that you can attack a DNS infrastructure. Okay, how does it look like? What are the important parts of your DNS server? Can you enumerate some? Of course, you have your DNS server itself, which contains your data. Okay, we call this data as your resource records. Those are the actual mappings. For this domain, say www.apnic.net, it resolves to this IP address. It is added into what we call as a zone file. It can be just a text file or it can be in a database, but it's essentially a mapping, right? So that's your DNS data. Someone can maybe compromise the DNS server, edit, make changes, or insert new information into your zone file so that it resolves to a wrong server or to a wrong machine. What else can happen? Okay, it can be the transaction between those DNS servers. In the DNS infrastructure, you have your authoritative server. Okay, in that authoritative server, it can actually be 2 or more servers. All of them are authoritative. All of them can answer questions. So basically, the way DNS works is you go to your own DNS server. It will do a recursive query from the root going down to the TLD, going down up to it reaches the authoritative server. When it reaches the authoritative server, it will give you the answer, right? Because it's the one who's authoritative to give you the information that you needed. So what can go wrong with that? Okay, possibly, say you have 5 authoritative servers, for example. Maybe, okay, the primary, this is where you make most of your changes in your zone file, in your zone data, and then it has to be transferred to all the secondary name servers. What if someone pretends to be a secondary? Or what if someone pretends to be a primary so that the information that is passed between them is wrong or totally a different zone file? How can I know that a server is authoritative? It actually depends. So the simple way is you do a dig command. So you open up your command line, for example, or your terminal, and you do a dig at, say, a server, and then the domain. Say dig at ns.apnic.net for training.apnic.net. And then the answer will give you some flag bits. One of them is AA. Okay, it says authoritative answer, meaning it comes from the authoritative server. Okay, so but basically the infrastructure itself will do the recursive query for you. So you have your own DNS server for your company. Okay, that's the one that you configure on your machine. Say in your Windows machine, you have their primary name server and then secondary name server. So your Windows machine will pull that DNS server. That's not the authoritative server, right? That is the recursive server. This recursive server will go to the root. It knows how to go to the root. And then the root knows the top level domain, so it will do a kind of like a redirection or a referral. And then from the top level domain, there's records that links the smaller or the lower server that leads to the authoritative server. So basically, there's a linking between the root going to the authoritative server. So it knows if you have reached the right server to ask the question. So that is kind of like not totally up to the user itself, but it's the system that can know that. But if you want to just like quickly do a check, dig command, or NS lookup sometimes can also give you that, but yeah, dig command is the best utility that you can use. That answers your question, Robertson? All right, hopefully. Okay, any follow-up questions, just write them down. Next one. Okay, still on the DNS data itself. So we know that information in your zone file, your zone data, or the resource record is important. It has to be correct. Now the question for you, do you know or do you have a way to verify that it is correct? You do a simple query, the authoritative server gives you the answer. How can you validate? There's no way. You just know that it came from the authoritative server. Okay, so that is one of the issues for DNS. There's no way to check the validity of the DNS data. Okay, so this one can be exploited. As an example, the cache poisoning attack, okay, is an attack towards this. If you remember, there are 3 goals in security: confidentiality, integrity, and availability. With DNS data, you don't really need to provide confidentiality. Why? DNS data is public data. However, you need to check that the information is correct. So integrity check. But is this provided with the typical DNS functionalities? Not quite. Okay, there are ways that you can on top of this, but just as part of the DNS protocol itself, not really. Okay, so that can be a problem. Another one is the DNS transactions. As I've said, for your authoritative servers, you have 2, 3, or maybe even more authoritative servers. Okay, so that one is down. You have others that can answer your question. The problem there is when they're interacting with each other, when they're sending these zone files to each other. How do you know that no one has or was able to maybe sniff into the conversation, or maybe someone has pretended to be the primary or the secondary to give you the wrong one? So that is another issue. DNS transactions can be compromised. Any questions? So if that wasn't clear, I have this diagram. Okay, let me just complete this so that it's easy. Okay, let me remove that one first. So this is how DNS data flows. The DNS infrastructure consists of your machine. Your machine, its operating system, is also acting as a resolver. Okay, but resolvers cannot do recursive queries. So it has to contact or communicate with a recursive or caching server, which is this one. You can see the arrow, right? Now from this caching server, it will go to the internet, go to the root server until it finds the authoritative server. This one, the master and slave, or we also call as primary and secondary. These are your authoritative server. This caching or recursive server will query either one of these servers. Okay, they're all authoritative. Now internally, one of these servers is acting as a master and the others are slave, right? So that you can sync the information that is coming from the primary towards the slaves or the secondaries. The content of the master is what you call your zone file. Again, it can be a text file or a database. Okay, but basically it resides on your master. You can do changes in this zone file either manually, static, or using dynamic updates. So what can go wrong here? These are the possible vulnerabilities. As you can see, it's everywhere. Someone can impersonate this cache so that it gives you wrong information. This is your machine, right? Someone can also pollute the information that is in your authoritative server. We call that as cache pollution. So the information may not be coming directly from this authoritative server, but what goes into here is totally incorrect. What else? Someone can compromise the machine itself, your DNS server, and corrupt the data, corrupt the zone file. Someone can pretend to be authoritative to make dynamic updates. These issues, okay, can happen simply by doing IP address spoofing. I'll pretend to be this. This is my IP address. What are the sort of things like security that you can do to limit who can access this master and slave? You can limit it based on the IP address. But again, IP addresses can be spoofed. Okay, most of the time, say who can access my DNS server? Only my local network, or only the IP block that is assigned for my NOC. But again, IP address can be spoofed. So impersonating master or slave here, I can pretend to be the slave. This is my IP address. I'll pull all of the information that's coming from the master. So what are we showing here is everywhere in your DNS infrastructure there are possible vulnerabilities. And how do we protect our DNS servers? We have kind of categorized them into two. One is looking at the interaction, the transactions that are happening between servers. We call that as server protection. Another one is focused on the content, on the zone data. Okay, make sure that it is correct and can be validated. This is what we call as data protection. Does it make sense for now? Okay, so one is the transactions between the servers. You have to verify who you're communicating with. And the other one, data protection, is verifying the actual content, the actual zone data or resource record that you received. All right, this is the cache poisoning example that I mentioned in the previous slide. So let me just load the entire thing. So this one is a typical DNS transaction. Okay, you have your machine, your client. We also call it as your resolver. And then it tries to resolve, okay, say for this one, it tries to look for the IP address of example.com. So it goes to the recursive server. Recursive servers are also normally caching servers. So that if you have multiple clients, okay, this server doesn't have to do the query every time. It has it in the cache and can give you the answer straight away until its TTL expires. Now the typical transaction goes from this recursive, okay, going to the internet or the rest of the DNS infrastructure is to go to the root, go to the top level domain, and then go down until it reaches this authoritative name server, which is ns.example.com. Okay, now this has the right answer. Say the IP address for example.com is this, IPv4 and IPv6 address. Reply back to the caching server, and this will be forwarded to the client. Now, obviously, you don't just get one query every time for this DNS server. It will get more. It will have heaps. So each transaction will have a particular query ID. So when the answer arrives, it knows that, yes, this is the answer for this particular question. So what is the problem here? In the earlier versions or implementations of DNS, this QID or query ID is sequential. So if right now this is 64571, right? The next query will be 64572, 64573, 74, etc. So it's easy to guess. If you are an attacker, once you know this query ID, you can bombard the DNS server with multiple responses, hoping that one of the responses will match the actual query ID. So that's what we're doing with cache poisoning. See here, this server is pretending to be the authoritative server, and then it responds with a lot of responses, and then one of the QIDs will match. What will make this worse is if DNS server is also an open resolver, meaning there's no restriction whatsoever who can access or who can query the server. Anyone from the internet can query. So what I'll be doing in that case is I will query the DNS server first so I can sniff, okay, the packet so I'll know the query ID. So now I have like a limited set that I can try, which means there are more chances that I can get it right. Yes, and this is all automated too. Okay, so it should be pretty fast and easy to do. So once you've done that and it matches, it will be accepted by this DNS server, and then my client will now communicate to the bogus website. It may look like your bank website or your company website, and you're enticed to input your information, your credentials, username and password, maybe your credit card details, and so on. That was the idea here. Okay, usually when you get an attack, it's not just a single attack. The idea is you have this attack and then it's followed by a few others. So in this case, the first one will be DNS cache poisoning, so that client are redirected to a web server, and then this web server can be maybe I don't know, hosting a malware, or yeah, maybe just wanting to get information from you that they can sell on the black market and things like that. So that can be a problem. Now this server will still reply, but this type of attack is normally targeted, meaning this attacker is sitting close to the cache. So the responses will come sooner, okay, less latency as opposed to this one. So once I've compromised or I've poisoned this cache, for some time it will give wrong information to my clients. Any question on DNS cache poisoning? So this was a big problem in around 5 years ago, if I'm not mistaken. Okay, and this actually makes it or like hastened the implementation of DNSSEC. We will discuss DNSSEC in just a little bit. Other forms of attack with DNS is DNS amplification. Now this is part of the ongoing issue with UDP. You know what's UDP, right? UDP is a connectionless oriented protocol, meaning you don't have to establish the connection first, and you can easily spoof source addresses. So it exploits that. So actually it's not just DNS, even NTP was an issue for a while, and then there's a few others, SSDP and stuff like that. Now what is this exactly? So someone can send you, okay, can send multiple responses to a target, but okay, these responses, okay, are because the source of the query is using spoofed IP address. So think of it that way. I need to query for example.com again. This is typical query. It goes to the DNS server. Think of that, but you have multiple bots, okay? Multiple clients that are querying all at the same time. And they're all using spoofed IP address. So it goes to the DNS server replies. When the reply comes, it will not go to those individual machines that did the query, but it goes to a target machine. The spoof IP address is an IP address of an actual target. Okay, so it's redirected to that target. It's a DDoS attack. Okay, it's a denial of service attack. You're trying to bombard that server with multiple responses. Now, what makes this worse is with DNS, typically, if you send a query, you can try that. Do a simple dig. Do a query. Your actual query will just be a few bytes, even a few kilobytes. But the responses are much bigger. Maybe you send a 100-byte query, the response will be maybe 100 kilobytes, or maybe even bigger. So that's why we call it as amplification. So it's both a reflection attack, meaning the responses goes to a target machine, reflected towards a target machine, and the responses are also amplified. Okay, the query is much smaller than the response it gets. So that means you have, say, if you have 1,000 bots, each one sending only about 10 bytes. That already corresponds to about, I guess, 100 meg, right? Now, if it's even if the responses are bigger, it can be in the gigabits of data going into your target. That's the DNS amplification attack. There have been quite a lot of attacks. Can't remember which one is the biggest, but there were a few over the last years. Even the ones just recently that happened this year is an example of DNS amplification attack. Okay, one of the biggest types of attacks, DDoS attacks that have happened. So this is how it looks like. I won't go through the details, but essentially this is like this. I've already discussed this. It goes to the root, responds, but it doesn't respond to these machines because they're all compromised machines. Instead, the responses are going to the victim. That's how it works. So the victim here is bombarded with large amounts of DNS responses. This is a DDoS attack. Any questions? So we've covered two common types of DNS attacks: DNS amplification and DNS cache poisoning. Can you please give a recent example of serious DNS attack? Well, one is, I'm just trying to remember which ones happened this year. One that I can think of on top of my head is DNS amplification attack that happened with, what's that? There is a Cloudflare article about DNS amplification, which they helped an organization. I think that was in around 2012, and the responses was about, I'd say, around 400 or 500 Gbps. That's a type of DNS amplification attack. You can search that. It's I can't remember exactly to which company on top of my head, but that's a big one. That was in 2012. Another is a DNS amplification attack on OpenDNS that happened in around 2014 or 2015, if I'm not mistaken. So you can look that up. The one that happened with OpenDNS lately, I can't remember if it's a DNS attack or an IoT attack. I don't think it's DNS attack, but it's targeted towards DNS servers, but it's actually multiple queries from IoT devices. But you can kind of consider that as well, but it doesn't fall under DNS amplification. Okay, so maybe I can like list down some of those attacks in a little bit. Let me just try and organize my thoughts about those incidents, and I can write them down here. So yeah, as Mike said there, the DYNE attack was actually IoT devices. Yeah, that attack is one of the biggest. I think that is considered the biggest DDoS attack on record, which reached about 1 terabyte, 1 Tbps. So that's a really huge one. So it targets two things, right? DNS servers and also IoT devices. And as you know, okay, we're going towards that phase where we're using a lot of IoT devices that are not protected. They're using default passwords, easy to attack, etc. So they're very good attack targets. Okay, questions, other questions, or anyone who has an idea of examples of DNS attacks? Okay, right. I don't see any more responses there. Okay, so let's continue this. Alright, let's go to the next one. Alright, open resolvers. Now, I will have to warn you, if you are ever running a DNS server, please don't run an open resolver. Okay, don't ever run an open resolver. What does that mean? Okay, as I've told you in the DNS cache poisoning example, it is aggravated more if you're running an open resolver, meaning you are running a DNS server that's open to everyone. It's connected to the internet and everyone can query, meaning you don't have any access lists or any filters in place. Generally, when you run a DNS server, you only allow your own network to use the DNS server. Okay, you limit who can access the DNS server. Otherwise, it can be used as a, not as just an attack target, but for other types of attacks. Somehow uses your open resolver in some way. So like first 2-3 steps will be querying DNS servers and stuff like that. So don't run an open resolver. Now, if you want to know, there's this project, openresolverproject.org, which lists all, well, basically not all, but it has a, it runs a kind of like a program that queries the internet and looks for open port 53. Usually, if you're running a DNS server, you're running it in port 53 because that's the default, right? UDP port 53 or TCP port 53. So with this one, you can see that there are like millions. I'm not sure if I have the graph here. Yep, this one. So this one was a snapshot earlier this year. But as of May 2016, that's still about 17 million open resolvers. This is actually much smaller than before. So as a comparison, in 2014, so 2 years before that, that's about 25 million open resolvers out there. Now your question may be, well, I'm using Google DNS. Is Google DNS or even OpenDNS is also running this? Are they open resolvers? Yes, they are. Okay, but obviously they have mechanisms in place to put up some protection if their open DNS servers are being used, okay, or being abused. But most of us don't have that. So it's not a good practice to run open resolvers. So whenever you install one or you deploy a DNS server, make sure that you limit the transactions or limit who can access your DNS servers. Right? Another one is DNS changer. And this is quite, it's a very practical type of attack, really, because you know that you can steer anyone to anywhere on the network as long as you can influence its DNS server, its DNS settings. So what it does is it runs a malware on your computer. It changes DNS, okay, the DNS settings that points now to their own DNS server, the criminals' DNS servers, so that when you do your typical query, the answer will be wrong. Okay, it gives you a totally wrong answer that leads to a fake website. So that's how it works. But it has become a big problem in, was it 2014 or 2013, such that there's lots of people in the security community that was looking into this problem. Okay, so many infected computers, so many infected machines. I don't have the statistics here anymore, but you can find it. DCWG is a working group, okay, that investigated this. At the end of the investigation, I think there were a few people that were charged with a case on the US court because they're running those fake DNS servers. DNS hijacking is another one. This is also called as DNS redirection. What is this? You have your users' DNS settings modified for malware, such as in the case of the DNS changer, or the DNS server has been compromised to provide you with incorrect responses. Okay, so your DNS server, okay, has been compromised. The information there has been changed, pointing to another machine, a fake machine. That is DNS hijacking. Okay. So now the question is, there's too many things that we can discuss about this combination of attacks that uses DNS and all other forms of known attacks out there, and the purpose is either denial of service attack or to compromise you or to fake websites and things like that. But the question that we have here, and we want to answer because we're like 20 minutes to go before the end of this session, is how do you now secure your DNS servers? Okay, there are many ways that you can do this. I only listed here a few, and I guess these are the most common or the easiest ones that you can employ. One is, depending on your operating system, depending on your DNS software that you're using, obviously you want to run the most recent version of your DNS software. You don't have to run, say for example, bind is the most common. Okay, what is the current version of DNS software? There's not just one DNS software. There are many DNS software out there. The most popular one is bind, DNS bind. Okay, so with bind, what version are they running now? Maybe 9.10 point something. Okay, but the idea really is just to make sure that you are running the latest version, not the deprecated ones. Let's say now you're using 9.10, but you're still running 9.4, even 9.3, which doesn't have support for even DNSSEC. So that's not good, right? Now you don't have to run the latest version, but make sure, say you have 9.11, but you're still running 9.10. Just make sure that it has the latest one for that particular version, and if there are patches available, particularly DNS patches, make sure to implement that. You'll know if it's a security patch. Okay, if it is a security patch, you have to implement it straight away. Otherwise, you might be a target for zero-day exploits. Okay, so okay, good. There's a few more DNS software out there. I generally use DNS bind. Okay, you can also use the one by NLNet Labs. Okay, those are also very common, depending on what you want to do. Do you want to implement an authoritative server? Do you want to implement maybe only a caching or recursive server? So NSD, Power DNS, of course Microsoft DNS will always be there. There are some of the common ones. Next is to, as I've said, restrict queries. The example of not doing this is the Open Resolver. When do you restrict queries? For example, for the typical query, okay, you only limit it to your clients, to your customers. Another one is limiting who can do transactions with your servers. Okay, which IP address, okay, can access and do what we call as zone transfer from primary to your secondary. Your primary should know who are its secondary servers, in the same way that your secondary should know who are its primary servers. So you're limiting it to that. If I have a machine here, if I don't have any restrictions or any ACL, I can quickly do a dig AXFR or zone transfer, and I can get a copy of your entire zone information. Is that good or not? As we said, DNS data is public data. Okay, so I guess it's okay if someone can get a copy of my entire zone file. Actually, no. Why? Because it usually maps your entire network infrastructure. So you know which ones are your DNS servers, which one's your mail server. If you have internal servers, sometimes it's also in your zone information. So as much as you can, you don't want to just hand over your entire zone file to everyone. Okay, that's why you should restrict who can do zone transfers. Okay, to your primary or to your secondary servers. If you're running bind, particularly you want to run it with the least privilege. Maybe you want to jail it or chroot. So that's one way to restrict access to it. So if you're running a server and it hosts other types of services, if your DNS server has been compromised, it's only limited into that box because it's jailed. It doesn't affect all other services. You can do things like randomized source ports as well. Now, by default, this is already being done, but the reason the DNS cache poisoning was very popular because of the lack of randomization before with query IDs and also with ports. So by default, nowadays, most DNS software implements randomization. If not, try to find a way for you to do that. Obviously, everything relies on the box itself, whether you're running Linux, Windows, or Unix machines. Make sure to always, of course, secure the box itself. And the last one, which is our main focus, okay, that is DNS specific, is using either TSIG, transaction signature, or DNSSEC, DNS security extensions. So what are they? You've shown the example. I'm not sure if I have that here yet. You've seen this diagram before where we showed you the vulnerabilities for each part. Now here, how can we protect them? We categorize them into two, server protection and data protection. With server protection, these has to do with transactions, right? So we can use TSIG for this. What can we avoid here? We can avoid issues with impersonation and unauthorized changes, unauthorized transfers, and updates to your DNS data. So basically, you're protecting or you're trying to validate the communication between two machines, master to slave or master to another machine that wants to do either query or transfers to your authoritative servers. Okay? How do you implement that? My examples here, I think the following slides, is specific to Bind, but most of the DNS software will have similar features. Now, let's go to the details of DNS transactions first. It's not just TSIG, but our focus is this one. But other ways that you can provide these types of protection is one, by using RNDC, Remote Named Controller. For this one, actually you can, this is particular to Bind, right? So you can remotely stop, start, reload your DNS server. You don't have to always stop the entire process itself, okay? But you can kind of like run it remotely. Okay, you run it on other machines. You can also use it from the machine itself, but that means you're not killing the process itself. You're just like using these commands so that it doesn't interrupt the entire operations. Okay, by implementing this, okay, you can like limit who will have this like control over your name daemon. How do you do that? By using symmetric key algorithm. What is symmetric key algorithm? You generate a private key. You give that private key only to the machines that are allowed to do that function. Okay, so that's our shared key or our private key. We share that only to the machines that are allowed to do certain functions to our DNS server. Okay, same thing actually happens with transaction signature with TSIG. This one is generally between your primary and secondary servers. Now, so far, the type of protection that I've told you about is by using ACL. You're limiting this transaction by saying that, okay, I'm the primary server, these are my secondaries, these IP addresses are the only ones that can request zone transfers from my primary. Okay, but again, that is based on the IP address. IP addresses can be spoofed. So what you can do is, again, use symmetric algorithm. You will provide the shared key, you generate that shared key, you provide it to your secondary servers. The secondary servers will configure their machine so that when they transact with this primary, they will say that, hey, let's use this shared key. The primary will then verify, okay, this is going to be the answer, but is this a a valid transaction. Is this coming from the right source? So it checks the shared key. If it matches, it can respond. Otherwise, the transaction will fail. Okay, SIG0 is another one. Okay, it's very similar to TSIG. It also protects these types of transactions. However, now we will be using asymmetric key algorithm. So you have a public and private key pair. An advantage to using asymmetric algorithm is you don't have to worry about how to share the private key securely. Okay, public key can be public, private key can remain private. Okay, but the idea is essentially the same. Now let's focus, I think, more on TSIG here. So what is TSIG again? It's a mechanism for protecting messages from primary to secondary. So I guess we already know that. It's all about zone transfers and dynamic updates. And how we can implement that is by using hashes, by using what we call as shared key that can be shared between your primary and your secondary. Now, to make that clear, it's something like this. It goes both ways. So, for example, I need to do a zone transfer. When we do zone transfer, if you have made changes in your primary or your master. Now, the zone transfer are usually initiated by your slave. Slave will check the primary. Hey, has there been changes in the zone file? If there are changes, I will request for a zone transfer. So this is that request. Query the master and ask for zone transfer. Now with this query itself, the key, okay, this shared key is attached to the query. The master receives it. The master will verify first whether the signature or the key is the same, and then it will respond to the requests going to the slave. Now the response itself also has a attached key, so that the slave or the secondary can now also verify that the response is correct. So it's two-way. The query going to the master is checked or verified. The responses coming from the master going to the slave is also verified. So you know that they are communicating, both of them are communicating to the right master and the right slave. Does that make sense? I see people asking questions or maybe typing something. Please go ahead. But basically the idea is this. Do you have an example? Well, this is the concept part. If you do understand the concept, then we can look at the example. Is the concept clear, everyone? So basically the idea is we have the shared key. For my query, before I go to the master, I will attach the key. Okay, so that the master can verify. Now on the other side, okay, the master verifies it before it responds. When it gets back to the secondary, it also verifies. Does it encrypt the packet? No, it doesn't. Okay, so no encryption here. Generally, encryption is not a big thing with DNS, so to speak. In some cases, they do encryption, but generally not, because the idea with DNS security is not to encrypt data or to limit who can access the actual DNS data, but to verify. So our focus is integrity, not confidentiality. Okay? Alright, sorry, I don't have the example here because this is the e-learning. But if you want to see the configuration for NameD, please shoot me an email and I can send it to you. I just don't have the information ready here, but the idea is I will configure, okay, I will configure my machine. This is done both on the primary and the secondary. In the primary server, I will say that this is my key. Say, for example, I will name this key as ns1 to ns2.example.com. So basically, that's the key name that I will, this is a scripted one, that I can use for transaction between my server, maybe ns1, and ns2, my secondary server. And then I will provide the actual key itself, the algorithm that's used for that. And then I have my zone statement. In that zone statement, you have usually your access list. You limit who can do the zone transfer for that. Okay. Now, instead of putting the IP address there, you will add the name of the key. Okay, so that's pretty much it. That's just like two statements added into your DNS named.conf, in your DNS configuration for both the primary and your secondary. So if you know how to do access, like limiting zone transfers, but adding IP address, it's essentially the same, except that you're replacing the IP address with the public address, the shared key itself, the private key. Does that make sense? I'm sorry, I don't usually add the configuration here, partly because we have limited time to do that. But again, if you want to see the example itself, I can send you. Or you can go to training.apnic.net, by the way. You can download the generic slides that we have for our DNS workshop, and I have some examples added there. So you can look that up. Loading up my machine. This DNS. So this one, sorry, I'm gonna type in the link here so that you can have a look by yourselves. So I'll leave you to go through that. There's so much information in the slide set, but somewhere there is some examples for configuring TSIG. Even DNSSEC examples are also there. All right, so I hope that answers your question, Robertson and Paul. Now let's go to the next one. So TSIG, we already know what the function is. Now one thing to remember with TSIG is you add the changes or the configurations in your DNS named.conf if it's valid. Now for the other one, which is data, you add most of the changes in the zone file itself. Actually, we might not have enough time to discuss the details of DNSSEC here, but let's look at the main concept. What are we trying to do? We are trying to protect the data itself. If I receive an answer, so I have a question, hey, what is the IP address of example.com? And then the response comes back. The IP address is 192.168.1.1. What do I normally do? I believe that. I use it, and yeah, I consider it as resolved, and I use it. Okay, my machine uses it. Now, did I verify it? No, not really. But I trusted the hierarchy, the DNS hierarchy, to give me the right information, and I know that it's coming from the authoritative Nameserver. But actually, that's not enough. Cryptographically, we can add more protection. We can add some form of verification. And that's what we're trying to do here. Okay? That's what we're trying to do with DNSSEC. DNSSEC stands for DNS Security Extensions. So actually, unlike with TSIG, with DNSSEC, we have now a new protocol, okay, kind of like an extended or an extension to our DNS protocol. Okay, you see this? RFC 4033, 4034, and 4035. These are the RFCs that defines DNSSEC in detail. So what's the idea behind it? Simple. You want to protect the integrity of your DNS data. As I've said, if you receive an answer, how do you verify? Okay, now a few things are included here. One is establishing a chain of trust, and another one is by digitally signing your data. You know the idea of digital signing, right? So for example, I am sending an email. I can digitally sign my email so that it can be verified by the other party. Okay? You know that, right? So that's digital signing. Essentially, what we're using there is asymmetric key cryptography, the use of public and private key pair. I use my private key to sign the data, send it over to the recipient. The recipient can use my public key to now verify it. Alright? So I hope you do understand the concept of asymmetric key cryptography or public key cryptography, because DNS relies heavily on that. Okay? So what you're doing is DNS data verification. How? We sign the actual DNS data itself. And the other one is using chain of trust. Alright? DNS is actually, it's a very big concept, so I can understand that you cannot get everything in just one sitting like this. That's why I'm explaining you the basic idea behind it. What are we trying to do with DNSSEC? You are signing data. So what is the output of that? You'll have your actual data. You'll have a signature of that data. Both of that will be sent when you do your typical query. Okay, and once it's received, okay, say on the recipient side, it has the data, which is, it's not encrypted. It's just like typical clear text format. But you also have the signature. Okay, now those two records, once you have that, you can do the verification. What else do you need to verify that? You of course need the public key. Public key of what? The public key that's generated by the authoritative server. Use the public key, okay, on the data, and then compare that with the digital signature. Does that make sense? So basically, by doing that, we're establishing the authenticity of the data itself. We know that it came from the right source. Okay, we can rest assured that it's rightfully coming from this authoritative server, not from any malicious DNS server, and it delegates trust to third parties or parent zones. There's now a link between the parent and the child zones. Now we already have that in the typical DNS setting, but now we're using crypto to add that linkage, to verify that linkage between them. Does that make sense? Okay, so now how are we going to do that? So this is the easy version of this. One, you have resource records, right? Example of resource record is A record, pointer record, NS record, CNAME. Those are resource record. All those mappings are records. Those records will be signed. They will be signed using the private key. Okay, and then you will have to publish that. You'll publish two things. One is the signature itself. So you sign, you have an output signature, you publish that in DNS. Another is the public key. So you signed it with a private key, so you need the public key to verify it. That's why it's public and private key pair, right? You sign it with a private key, you send that to the public. When it's received, it will use the public key. That's why you also have to make the public key public. Okay? And then child zones will also sign their own set of records. Parent zones will not sign for the child. However, they will have a hash of the child zone's public key, and that will be used for the chain of trust. Okay, so basically this 2, 3 or 4 bullet points answers this question, establishing authenticity, and the last point is for trust, the chain of trust. I don't see anyone asking questions. Is this clear? Now, where do we implement DNSSEC? One is on the authoritative server. The other one is in your resolver. So there are two parts to it. Okay, the authoritative server will sign their zone data. The resolvers will do the validation. So those are the two endpoints. If you have, okay, a domain, you will sign your domain. Okay, if you have, or if your operating a DNS resolver, you want to verify those signed data from authoritative servers. So you will implement a validating resolver. Does that make sense? Okay. Now there are a few concepts that are related to this. To implement the concept, the idea of DNSSEC that we've covered in the last 2 slides, we'll have to introduce a few things in DNS. That's why, there's like additional extensions in your DNS, like there's new RFCs that were introduced by this. You now have new resource records. Okay, you now have the concept of chain of trust. You'll have to generate public and private key pairs, and you need to implement validation. Okay, these are the resource records, RRSIG, DNSKEY, DS, and NSEC 3. I'll explain that in detail when we look at, when we cover, if you join the session on just DNSSEC. Okay, I seem to have a problem with my video. Can we just stop that for a little bit and then I'll share that again with you? Alright, sorry, I think my video is gone, but hopefully you guys can still hear me. Okay, but I'll just continue with the discussion. Okay, please, if you can still hear me, just continue doing that. Sorry, no more video for this. So alright, where did we stop? We said you're introducing new resource records. So these resource records are what we call as RRSIG, DNSKEY, DS record, and we also have, what did I miss? NSEC or NSEC 3 records. So going back to, let me just quickly go back to, here's that. This one, okay? You should understand this. The idea of the resource record implements this. First, records are signed with a private key, and then the signature is published. This is your RRSIG. Public key is also published. This is your DNSKEY. Okay? Child zones also sign the records, basically just new RRSIGs. Then parent signs the hash. That hash that will be forwarded to your parent zone is your DS record. Okay? So that's what we mean here. The signature is your RRSIG. The public key is your DNSKEY. And then your parent will receive a DS record from you. So when you do a typical query, so going back, how do you make a query? You go to your resolver. Your resolver will go to the recursive server. Your recursive will do a typical query from the root going to the authoritative server. If I'm doing validation and say I queried for example.com, and example.com, okay, it's implementing DNSSEC. It's DNSSEC sign. That's the term that we use, DNSSEC sign. So if this domain is DNSSEC sign, what happens? My response, before, in a typical query, you only get, of course, the answer to your question. If you ask for an A record, you get the A record. Now, if you're doing DNSSEC, the answer that comes back to me is still the A record in its clear text format, and then it has an accompanying RRSIG, the actual signature. Now, it will also send me the DNS key so that I can do the DNSSEC validation. Clear enough? Okay, so I hope it clarifies it. Okay, again, the details, more details about DNSSEC I will cover in another session. If you want, you can also attend that. Now, just to wrap things up, I still have a few slides here where I show you some of the things that DNS can help with security. It's not exactly securing DNS itself, but it helps with securing other things. Okay, one is basically, well, this one is for DNS, response rate limiting. If you are worried of becoming a target of DNS amplification attack, okay, you can implement this. What is DNS amplification? You get a lot of queries, right? And you answer to all of these queries. With response rate limiting, you are limiting the number of queries that you are now responding to. So even if you get 10,000 queries because you are being attacked, okay, it will not affect you so much, your performance, because you're only going to answer maybe 5, 10, or even 100, okay, of those queries. Okay, so that's a protection against DNS amplification. Another one, this has got to do with email validation. If you've heard about SPF, Sender Policy Framework, okay, this is an example. For APNIC.net, basically, if I receive an email coming from APNIC.net, if I have a SPF, I should have an idea that this should only be coming from this trusted IP addresses. If not, then it's a source of, maybe it's something that has to be checked further. It's not trustworthy just by itself. Okay, so that helps with email verification, email validation. Another one that most of you should now look at and consider implementing is DANE, DNS-based authentication of named entities. What is this? We will have an additional record with DNS. We call it as TLSA. With this one, you can have certificates added as a kind of like you can say that it's a resource record. Okay, it's a secure method to associate a certificate that you got from a TLS server with your own domain that you are authoritative to answer. Okay, I think the last time I checked, it's still a proposed standard. However, it's been highly promoted already in the community. Okay, so you can find a lot of information about implementing DANE in your network. Another one is RPZ, Resource Policy Zone. This is specific to DNS bind. Okay, so basically the idea is having a reputation-based zone. It's kind of like making your DNS server act as a firewall. So it checks the reputation of the DNS servers before responding to it. Think of it as equivalent to DNS blacklisting for emails, for mail servers. Okay, the idea is you have this like set of DNS servers that has a corresponding like reputation, which is backed by the community, that can be updated. Okay, and then you can refer to that. And then if you receive query, you know that, hey, is this DNS server trustworthy? Okay, does it have a good reputation and things like that? So you can quite easily block any queries that are coming from sources that has bad reputation. That's DNS RPZ. And I think that's it. That's the entire coverage of this session on securing DNS. If you have questions, please write them down on the chat. I know we've already seen a lot of questions coming from this session, and I'm happy that this is quite interactive. But if you have more, please write them down on the chat.